Nyquist plots today. These are very beautiful things and very clever. So let us start with the S plane, by which I mean this is the real part of S, this is the imaginary part of S. S is a complex variable. There is a function g of S which maps points on the S plane to points on the G plane. So this is the G plane here. So for example, if you have some point S over here, it will get mapped to some point here. It need not be invertible. So for example, if I have a point G here, it may be mapped back to multiple points. That's not a problem. The forward mapping has to be single valued. That is all we want. In this mapping, we will be interested in something like some closed curve. Let me denote it by C. This closed curve will be mapped to some closed curve in the G plane, and that closed curve may of course self-intersect. It may be some complex curve like this, complicated curve like this. On this curve, if we have a direction of traversal like clockwise in this case, which you can see what it means, this may be counterclockwise also, it doesn't matter, but it will have a direction of traversal in that plane as well. This curve being C, we will call this curve G of C. So that's a curve now. Very good. We can define various functions of C that involve G. So for example, some examples of functions. Perimeter of G of C, area of G of C. Here you may have to assign plus or minus convention for clockwise, counterclockwise, something like that, but you can define an area. Okay. How about centroid of G of C? So this is a real number, this is a real number, this is a complex number, right? But we are not interested in these particular ones. These are just examples. Our main interest, f of C, is the number of clockwise encirclements of the origin in the G plane. Now you may wonder why we are interested in such a peculiar function, and there is a very nice reason. Okay, so let us start again with the S plane here. So that's S. Let's take some contour which we will traverse clockwise. This contour is C, and let us say that inside this contour there is a 0 of G and a pole of G and another pole of G, and of course G must have other poles like that and another 0 over here. Maybe it has a 0 here as well. Whatever it is, some poles and zeros are outside, some poles and zeros are inside, whatever may be the case. Now this f of C is the number of clockwise encirclements of the origin. You see, two bad things can happen. One is, for some S, G equal to 0. If that happens, then you see G of C will cut the origin, and if we perturb it a little bit this way or that, we may get one more or one less encirclement of the origin. Okay, so this is a special point. Another is, for some S, this goes to infinity. Okay, so this again, the curve goes off to infinity, then it comes back from infinity, and we don't know, it's no longer a closed curve, so we don't want these, so we will avoid these points. That means basically we will avoid zeros and poles of G. Very good. In that case, what happens is if I perturb this curve a little bit, I change it a little, maybe like this, maybe like this. In that case, G of C changes slightly also. But because none of these are changed, G of C, the number of encirclements, remains constant. So this function is actually an integer valued function. No difficulty so far. Now let us choose a special contour. The special contour we will choose goes along the imaginary axis. We will assume that there are no zeros and poles on the imaginary axis. If there are, we may have to make a little detour like that and leave that point out. But let's avoid that difficulty for the moment. And then close the loop with a big circle like this. So basically we are enclosing the entire right half plane for practical purposes. Basically, you know, zeros and right half plane zeros and right half plane poles of G are included in this contour. Then we make the contour bigger and bigger and we reach some kind of limiting value. If G is strictly proper, then G of infinity equal to 0. So over here, all of this gets mapped to 0. Otherwise it will get mapped to some constant probably, you know. So suppose if not, say G is s square plus 2 by s square plus 3s plus 5, so still proper, not strictly proper, then G of infinity equals 1. Okay, very good. Let us take this contour. Now what happens is we can deform the contour now. So what we will do is we will deform it so that we make a small circle around this, then we come like that. These two lines are meant to be very close. Okay, this one and this one, very close. So this is almost a complete circle clockwise. Then we come here, I hope you understand what we have done. F of C has not changed. Okay, now this one and this one will cancel, this one and this one will cancel. Why will they cancel? Because on this outward trip, whatever we do around the origin, on the backward trip we will do exactly the opposite. So the net number of encirclements of the origin will be 0 from this part and this part. Similarly from this part and this part, similarly from this part and this part, similarly from this part and this part. And then if you follow the clockwise convention, you will see there is a circle over here clockwise, another circle here clockwise, another circle here clockwise, another circle here clockwise, and another circle here clockwise. And therefore f of C is basically the sum of encirclements due to infinitesimal circles around each right half plane, 0 and pole. Very good. So this is what we have to understand now. Okay, so here we go. Let's say this is a 0 and this is a pole. Sorry, this is a pole here. So there's another pole there, another 0 there, and many other zeros and poles. Doesn't matter. So let's say G, this is the S plane here. So let's say G is some number A times S minus Z1 times S minus Z2 times S minus Zm. So there are m zeros divided by S minus P1, S minus P2, S minus Pn. So there are n poles. Okay, very good. Let us consider what happens when we encircle this 0. Okay, so this point here is S. This little radius is small, its angle changes a lot, but from here the argument of this vector doesn't change much. It changes by an infinitesimal amount only. Okay, so over here when I am traversing this small circle, what does G look like? Let's say that is Z1, it is the 0 Z1. Then this looks like A S minus Z1, but for this one, or for this 0 which is Z2, this vector just looks like Z1 minus Z2. So Z1 minus Z2, Z1 minus Zm, Z1 minus P1, Z1 minus P2, Z1 minus Pn. And what I will do now is I will take this and all of this, and it's just a number, right, independent of S, S minus Z1. And what is S minus Z1? S is equal to Z1 plus some small number r times e to the power minus I theta. Why is it minus I theta? Because as theta goes from 0 to 2 pi, I want it to travel clockwise, not counterclockwise. Okay, so therefore this becomes B r e to the power minus I theta. That's what G is. Okay, and then this is just some number, it's a complex number, it doesn't matter what it is. This part means 1 clockwise encirclement. If this was rotated, then this would be squared. I'm sorry, not repeated, not rotated. If this was repeated, then this would be squared. If this was squared, this would still be the same, but this would be squared. This would be 2 theta, and we will get 2 encirclements. No problem. Okay. Therefore, in f of C, we get number of RHP zeros of G, and then we have to find out the contribution from the poles, and it will be minus number of RHP poles of G, and we will see that soon enough. What will happen is, now suppose this is the pole Z1, sorry, P1. In that case, we will have A P1 minus Z1, P1 minus Z2, P1 minus Zm over here from this term s minus p1, because its argument changes a lot, and then p1 minus p2, p1 minus pn, and we will take all of this and call it some number b prime by s minus p1, but s is equal to p1 plus some r e to the power minus I theta. Therefore we will have b1 by r e to the power I theta, and as theta goes, because this was in the denominator, so it will come up and then it will become e to the power I theta. This is just some number b1 by r, and so as theta goes from 0 to 2 pi, this will be a CCW, counterclockwise encirclement, equal to 1 counterclockwise is equal to minus 1 clockwise encirclement. That is what leads to, we wrote this somewhere, but we will write it again. So f of c for this contour is equal to number of right half plane zeros of G minus number of right half plane poles of G. Okay, what does this have to do with control? Alright, so we are interested in feedback, and we are interested in the closed loop transfer function, which is kg over 1 plus kg with unit feedback, unit gain in the feedback loop. Yes, but let us just think of this as g right now. So let's just say g over 1 plus g. So in this case, give me just a second. Sorry about that. So in this case, what happens is, when we look at the mapping 1 plus g, right, that just shifts g a little bit. It shifts the contour a bit to the right, the mapped contour, doesn't matter. But now if we look at it, then the number of right half plane zeros of 1 plus g minus the number of right half plane poles of 1 plus g, this, if you think about it, is exactly equal to the number of closed loop poles, right? Because wherever this is 0, there you have a closed loop pole, and wherever you have a pole of this, that means this is infinite, that means this is infinite, so you have an open loop pole. So minus number of open loop poles. Okay, that is what this means. Now what is interesting is that when you look at the mapping of 1 plus g and talk about the origin there, that means 1 plus g equal to 0, this is the same as saying g equal to minus 1. And so you don't even have to map 1 plus g, you just map g and you count clockwise encirclements of the point minus 1. Okay, so if you take clockwise encirclements of the point minus 1, that's enough. And so what we will do here is we will take transfer function g, then we will take this contour, we will get some contour here which will be in the g plane, this is the s plane. This contour will be symmetrical, so maybe it will look like this. I'm just trying something. And maybe the point -1 will be here, and maybe this direction is like this. So we will start at any point. We can start here, for example. So we will come here and come here, 1, 2, 2 clockwise encirclements. Okay, so this plot is called the Nyquist plot. MATLAB plots it. There is a built-in command. Okay, now let me show you some examples in MATLAB and show you how it relates to stability analysis. I will point out to you before we do that over here, once again we are looking at this axis. That means S is equal to I omega. Over here, G of S equals a constant. For a strictly proper transfer function, it is in fact equal to 0. Okay, but over here we don't require G to be stable. For the Bode plot we required it to be stable, but over here we can mathematically plot it even if G is not a stable plant. If G is a stable plant, then in fact we can just evaluate it on the frequency domain by even testing, just like for the Bode plot, as I had explained earlier. Let me show you in MATLAB how this G works. So S equals this trick we have used. Let me take a random one. Okay, no, not this. G equals, so here is a random one. You see it will have 5 poles and 2 zeros. Okay, so this is some random one. I can make the root locus plot of G, and you will see this is a nice one. You will see 1 pole here, 1 pole here, 1 pole here, 1 pole here, and 1 pole here. So in this system nothing really changes in the root locus plot. There were 2 right half plane poles for the open loop system, and then 2 right half plane poles for the closed loop system for all values of k. Let me explain to you what k here means. So suppose this is what we have for G, then for kg with k equal to half, what do we have? We will just have half of that, isn't it? So we will have, you know, this shape here. Well, maybe not half, maybe that's 1/3 or something, you know. So this is kg for k less than 1. So when we draw 1, we can imagine it for all k's. Okay, so that is an advantage of the Nyquist plot. So when we come here in this root locus plot, it is clear that there is no k for which the number of closed loop poles is going to be different from the number of open loop poles. So when I come here and draw the Nyquist plot, you will see that that is indeed the case, because the Nyquist plot looks like this. And you can see it is all on the right hand side. There is even an arrow given here. The arrow is sometimes a bit hard to read. In this case it is easy to read. But you can see that if I have negative gain, or if G is minus G, then this structure, this one, will get flipped to the other side, and then we will have interesting things. So let me say G is equal to minus G. So this is a new plant, some random plant. Now if I make the root locus of G, you will see more interesting things here. Okay, so you will see once again 1 here, 1, 2, 3, 4, 5 poles, right, and 2 zeros here. In the right half plane, 2 poles to begin with, let us zoom in over here because that is where our interest lies for the moment, and you will see that once in the closed loop, once I start increasing k, okay, at a gain of 0.223, two poles cross over to the right hand side. At a gain of 5.35, these two come in, and these two which have gone out, this gain of 0.73, one of them comes back in. This is what we are seeing in the root locus plot. So we start with two poles in the right half plane, then at a gain of 0.223, 221, we have 4 in the right half plane. So let's write that down, okay. K equals 0, 2 poles right half plane, K equals 0.223, 4 poles right half plane, K equals 0.73, 3 poles in the right half plane, and K equals 5.36, 2 of them are back in, so only 1 pole in the right half plane. Okay, so let us first try K equals 0.17 or something in between. Okay, we have started with 2 poles in the right half plane. That is the open loop system. We know how that behaves. So let us do Nyquist 0.17 times G, and when we look at the Nyquist plot, let us move it here, you will see this plus here is -1. There's a small red plus here, no encirclements, so no problem. That means no change. The number of closed loop poles is equal to the number of open loop poles. Very good, no change. We come here, 0.223, let's use 0.3. Now 2 more have gone in, okay, to the right half plane. So 0.3, let's try here 0.3, and now we have to look here and see the number of encirclements. The arrow is clear, does something over here and comes around. So you see, if you can see my cursor, 1 encirclement, another encirclement, 2 clockwise encirclements. That means the number of closed loop poles which is now 4 minus the number of open loop poles, which was 2, is 2. That's consistent. Okay, now between here and here, let's try K equals 1. Okay, so when we try K equals 1, that's Nyquist of G. And now you see this little pool here, loop here, makes no difference. Overall there is only 1. Okay, what does that mean? That means the number of, we've crossed over here, right? K equals 1. That means the number of closed loop poles minus the number of open loop poles is 1, which is indeed the case. And now let us try K equals 6. And when we do that, we find here, so we have to zoom in, a tiny portion here, and when we zoom in, this arrow is going like this arrow is coming back out, and you see there is one clockwise encirclement. What does that mean? Or maybe the arrow is wrong. The arrow direction is wrong. So let's figure out the arrow direction. Let's look here. What is G for large S? For large S, G is some negative number S square by S to the power 5. Okay, so let's look here. I don't want that. I don't want that. Let's look here. Some negative number, does not matter. Large S, right? Some negative number, S square. What the negative number is does not matter, by S to the power 5. So we will cancel, it will be S cube. Let me go to the top. So I am increasing this part of my S plane. I am approaching G of S equals 0, but S is I omega. So this is I cube omega cube. This I cube, I will cancel a minus 1 and cancel this one. Then this I will come to the numerator with a minus I. So this is equal to minus I by omega cube. So you can see that asymptotically, as I am traversing this part of the contour on the G plane, I am coming to the origin like this. Okay. So once I know that, when I come here, this means I am traversing like this. This arrow is a bit misleading. So I am traversing like this. That means it is a counterclockwise traversal. Okay. And when I look out, nothing else is there. This is all there is. Okay. This is all there is. That arrow is misleading somehow. This arrow, look at it like this. This arrow is coming like this. One counterclockwise. That means minus 1 clockwise. If it is minus 1 clockwise, that means the number of closed loop poles minus the number of open loop poles is equal to minus 1. In this way, you can see how the Nyquist plot can be used to understand the closed loop stability of a plant, which may or may not be stable in open loop, yet you look at it in frequency domain. It is a mathematical mapping. For a stable plant, you can generate the Nyquist plot experimentally also, but for even an unstable plant, if you have the model, you can generate it numerically using a computer. And if you know the number of right half plane roots only, then you can understand or quantify the stability changes in the system as the feedback gain is changed, without actually computing what the poles are for all those k values. We will stop here.